Hi everyone, my name is Jonah and I'm a PhD student at the ANU, and today I'm going to be talking about the Pyxis interferometer. Exoplanets are quite the hot topic these days. We want to know more about their formation history, their demographics, and in particular about their atmospheres and whether they could potentially harbour alien life. Unfortunately, the techniques we use these days, the transit method and radial velocities, aren't really sensitive to Earth-like terrestrial planets around solar-type stars. What we'd really like to be able to do is to directly image these planets and get good spectra of their atmospheres. Unfortunately, that's easier said than done. The resolution requirements to separate these planets from their stars really require long baseline interferometry. However, these ground-based instruments are really insensitive. These stars outshine their planets by a factor of 10 million in the infrared to a factor of 10 billion in the visible, and thus we really need high signal to noise. To get around this, we can move into space and do space interferometry. That is, having a long baseline interferometer in space where you get both the resolution and sensitivity requirements to look at these planets. Space interferometry was studied a fair bit in the mid-2000s, particularly by ESA for the Darwin mission and NASA for the TPFI mission, but these were both cancelled due to budget cuts. There is a bit of a resurgence in the field now, though, with the LIFE initiative, which has been put forward as part of ESA's Voyage 2050 plan. Here at the ANU, we are now looking at building some technological pathfinders with the eventual goal of proving metrology and formation flying subsystems for this eventual LIFE mission. And that's what Pyxis is. Pyxis is a ground-based pathfinder for an eventual CubeSat mission we hope to launch within the decade, to then this final LIFE type mission. So let me go into a bit more detail about what Pyxis is. Pyxis is what we call a car park interferometer. That is, it's going to be 3 autonomous robots in the car park of Mount Stromlo Observatory, which will kind of act a bit like CubeSats. These robots, you can see one of the robots here on my poster, and each one has 3 wheels and 3 actuators to give fine 6-axis control, as well as a 7th gomiometer axis for really fine telescope control. The telescopes themselves are custom made, diamond turned out of solid aluminium, and this negates any thermally induced optical aberrations, which is a particular problem for satellites. We also have an angular control system using a star tracker to give sub-arc minute precision at greater than 2 Hertz to know where you're pointing. And especially important is the distance metrology, and this is the main subsystem we're testing for space. This gives very precise relative distances between the robots using a coarse time-of-flight photodiode system and then a much finer interferometric sensor which can give sub-micron precision using a photonic chip. Finally, the light from the telescopes is sent into a science beam combiner where we hope to get polarimetric and spectroscopic information from these fringes. This is also using a photonic chip based on a tricoupler design. So we're hoping each of these subsystems are being developed here as we speak, and we hope to integrate them all together sometime next year for on-sky testing in 2023. So stay tuned for more updates. Thank you.